All right, so now we're going to look at when you have electron pair geometries that have a lone pair. And so the molecular geometry is going to be different, okay, than the electron pair geometry. So for linear, there's no option for it to have a lone pair, okay. For trigonal planar, okay, when we take away one electron pair and it becomes a lone pair, the shape is different. Okay, so it goes from trigonal planar to bent. Okay, so I'm going to show you what that looks like. So bent would be like SO2 here. So see how normally you would have, this would be trigonal planar, you would have an electron pair here, and it would kind of look like that Mercedes symbol that I talked about earlier. Well, now it has an electron pair there. And so if you if you notice what happened before, you had angles of 120 degrees, and you still have them here too, but you end up having the molecular geometry becomes bent instead of trigonal planar. Okay, so again, the atoms are in the same plane, but because you lost an electron pair here, it becomes bent. And by the way, water also has this configuration, being bent. All right, but this is tetrahedral. We'll get to that in just a second. So when it's trigonal planar and it has one lone pair, its molecular geometry becomes bent. Its electron pair geometry is still trigonal planar, but its molecular geometry is referred to as bent. Okay. So when they ask you the electron pair geometry, you're always going to refer to the structure that has no lone pairs. Okay, and then if your structure happens to have one or more lone pairs, then its molecular geometry is going to be different than the electron pair geometry. All right, so let's go and move on to tetrahedral. So we know tetrahedral, what it looks like. Let me refer back to that. Methane is an example of tetrahedral geometry. So all the bond angles are at 109.5 degrees. Okay, so what happens whenever you lose an electron pair? So when we go from tetrahedral to ammonia here, this is referred to as trigonal pyramid. Okay, because trigonal, like it looks like a tripod, right? It has three bases here, three atoms base in the same plane. Okay, and it looks like a little pyramid. Now it's really hard to see here, but when you have some ball and stick fit models, it's more you can see how it kind of looks like it's a little pyramid. So it's a trigonal pyramid. And so the lone pair here created this. The molecular geometry is going to be different from the electron pair geometry. So electron pair geometry is tetrahedral, like that's the parent geometry, but the molecular geometry here is referred to as trigonal pyramid. Okay, so we see that here, trigonal pyramid. All right, what happens when you have two lone pairs? Okay, well then you end up with bent again. So if we look at something that has two lone pairs, SO2 is an example here. And actually with this, we'll go back to water. It's too low. Here, so this is a bent configuration, all right? Water is an example here. It has two sets of lone pairs. So it has four electron groups, just like tetrahedral would, but because it has two lone pairs, its molecular geometry is bent. Okay, so that's what you get with that. So if you have five electron pairs, you have trigonal bipyramid. And we've looked at this before, so we'll look at it again. Trigonal bipyramid, PCl5. All right, so here we see with trigonal, these atoms here that are in the same plane in the middle here, that sort of looks like trigonal planar, doesn't it? Okay, so trigonal bipyramidal, like I said earlier, you have trigonal, you have these three atoms in the same plane, and then you have an atom going above the plane and below the plane. Okay, so you have two different pyramids with three atoms as the base that are in the same plane, trigonal bipyramidal. All right, so if we lose an electron pair, and we don't really lose it, but we lose a bond, and instead it becomes a lone pair, we get this seesaw arrangement, which is shown as SF4. All right, so see, we still have we have 5 electron pairs, okay, but instead of having 5 bonds, we only have 4 with a 1 lone pair. And that creates what's called a seesaw arrangement. So if you notice, if you can imagine, if you have a seesaw with a base of 2 atoms there, and these guys are going up and down like a seesaw. With a molecular structure, with a Wallenstrom structure in person, it's a lot easier. It's not as floppy. But you can imagine these guys are going up and down like a seesaw with a base of 2 there. So this is referred to as seesaw for the molecular structure. An electron pair structure would be the same. It would always be trigonal bipyramidal because you have 5 electron pairs, but because one of those electron pairs is a lone pair, its molecular structure is seesaw. All right. The next one here we have T-shaped. So T-shaped is like ClF3. So here again we have 5 electron pairs, but its molecular geometry is T-shaped. It looks literally like the letter T. Okay, 9 degrees as the bonding angles to sets of lone pairs. And then if you lost another bond and replaced it with a lone pair, you would have linear again. XF2 is an example of that. Here we have 3 lone pairs, and the molecular geometry is linear. But again, its electron pair geometry would be referred to as still as trigonal bipyramid. Okay, but its molecular geometry is linear. All right. So the last type is called octahedral. SF6 is an example. With octahedral, again, you have this base, but instead of 3 atoms, you have 4 atoms. It looks like a square if you were to draw lines to each atom there, like a square base there. This is octahedral. You have an atom going up and above and below the plane of these 4 atoms there. And so if you were to lose a bonding pair with a non-bonding pair, this is what it would look like. And so this is referred to as square pyramid. So you see the base here. Bring this guy up here. The base is a square. Okay, it looks like a little pyramid, square pyramid. Okay, the lone pair is on the bottom there. Square pyramid. Now, if it has 2 lone pairs, it's square planar. It's just like a square there. If you were to draw lines to each atom, it's like a square. It's in the same plane, square planar. And then, if you were to add replace another bonding pair with a lone pair, let's see. You have T-shaped. Okay. Now, you would have, because this is T-shaped for another molecular geometry for trigonal bipyramid, but you would have an additional pair of lone pairs there. They just didn't have it on the simulation. But the molecular geometry would be T-shaped. But just imagine you would have an extra lone pair up here. But again, it looks like a T-shaped. And then if you were to have another pair of lone pairs, and imagine again another set of lone pairs here, you have linear for the molecular geometry. All right, so we've gone through this table here of the electron pair geometries. That's whenever you don't have any lone pairs on the central atom. And then when you start to have lone pairs, the geometry changes, and so you need to memorize that geometry as well. All right, so I'm going to go through a couple of examples here they have in the chapter. And the first thing you have to do when they're asking you to predict the electron pair geometry and the molecular structure, we know those are two different things, right? The electron pair geometry is when you have the geometry where there's no lone pairs on the central atom. It's sort of like the parent. What I think of as it's sort of like the parent geometry. And then the molecular structure is, it could be the same as the electron pair geometry, or if the structure ends up having lone pairs on the central atom, then it's going to be different from electron pair geometry. So here we have, we're having to draw out the Lewis dot structure. So I'm just going to scroll through the solutions here. So CO2, this is the Lewis dot structure for CO2. So it's electron pair geometry. It has basically two electron pairs. And so it's going to be linear. Okay. And then because there's no lone pairs on the central atom, its molecular structure is also going to be linear. Okay. Next, boron trichloride. Here's the Lewis dot structure for it. And so we have 3 electron pairs here. Okay. So its electron pair geometry should be trigonal planar, because there's, if it's 2, it's linear. If it's 3, it's trigonal planar. If there's 4 electron pairs, it's tetrahedral. If it's 5, it's trigonal bipyramid. If it's 6, it's octahedral. That's something you have to memorize. And again, you just memorize it from this first, or actually, you look at this second chart here, 2, 3, 4, 5, 6. Here's the electron pair geometries for that. All right, so here there's 3 electron pairs, so excluding you never count the central atom. So it's trigonal planar. And then we notice that since there are no lone pairs on the central atom, it is going to be, its molecular geometry is also going to be trigonal planar. Okay. All right, here this question is asking you pretty much the same thing to predict the electron pair geometry and molecular structure for ammonia. The ammonium ion. So ammonium ion is NH4+. So here's the Lewis structure for that. There are no lone pairs there, so its molecular structure and its electron pair geometry is going to be the same. Okay, so in this case it's going to be tetrahedral because it has 4 electron pairs. Okay, for the next one here, again, they're asking us to predict electron pair geometry and molecular structure. So here we see 1, 2, 3, 4 electron pairs. So its electron pair geometry is going to be tetrahedral. Okay, and then its molecular structure is going to be bent. Okay, because we have 2 lone pairs there. And if you look here on your table, again, 4 is tetrahedral, you have 2 lone pairs, the structure is bent. Okay, so sometimes if you draw out these structures and then you take away some of the bonding there, you can see how it looks like it's bent. Okay, so it just takes a little bit of practice to see that. And we know H2O has a bent molecular structure. So in this case, the molecular structure and electron pair geometry is different. The electron pair geometry is tetrahedral because there's 4 electron pairs, and the molecular structure is bent because it has two lone pairs. All right, last one here we have SF4. Okay, so here's a Lewis dot structure for that. We have 1, 2, 3, 4, 5 different electron pairs there. They're asking us to predict the electron pair geometry and the molecular structure. So we know when there's 5 electron pairs, it's trigonal bipyramid. Okay, and so it has, so it's electron pair geometry would be trigonal bipyramid, but its molecular structure would be seesaw. And you can kind of see that here. If you have, two atoms as a base, and then you have these guys going up and down, it kind of rocks. If you had a molecular structure, you could see it you can rock it back and forth like it is a seesaw. Okay, so this kind of looks like a seesaw portion where it's going up and down. It can go up and down because of this angle here. The way the angle is, it really does look like a seesaw. All right. Okay, one more here. We have, we're trying to figure out the electron pair geometry and molecular structure again for here XEF4. And so here's the Lewis dot structure for it. We can see we have 1, 2, 3, 4, 5, 6 electron pairs. So its molecular or its electron pair geometry would be octahedral because it has 6 electron pairs. But its molecular structure would be different because it has 2 lone pairs. This would be square planar. Okay, and again, you can see there are 4 atoms there that kind of look like they're in the same plane. So the molecular structure would be square planar, and the electron pair geometry would be octahedral. All right, so look through this section here. There are a couple more examples you can look through. We're not going to talk about dipole moments or anything like that. That's something that you're going to probably get into a little bit in next semester anyways if you take chemistry. But it's good to have a working knowledge of molecular geometry and electron pair geometry so that you're familiar with these different structures, because you may end up having to learn more about them next semester.